Okay, can you see that?
Yep.
Okay. Okay, so let's go over a few announcements regarding labs. As you all know, I'm sure 17 and 18 are this week's labs. So they'll be due next Monday, the 13th by midnight. And then next week, well, here and today, yeah, quiz 3 is still on. I've received so far 5 quizzes. And that's due by midnight. And then the class project, which we talked about last time, that's due Friday, May 8th. And I put a summary on Blackboard in the class project folder, and we'll have a look at that in a little bit. And then the next exam is next Wednesday, the 15th.
Mic off.
And see, that will be on Blackboard by 8 a.m. and then due by midnight. And it was supposed to cover all of 16 and all of 17, but we missed a week, and I think it'd be cramming in too much to put all of 17 on it. So it'll include most of 17. Like the later parts of it will be put on the next exam. And because of that lost week, we probably won't cover all of the coordination chemistry chapter. We'll cover the basics and then merge, like put the rest of 17 on the fourth exam. So the fourth exam will cover one full chapter and parts of 17, and then most of the coordination chemistry chapter. Oops, and I guess I should start that recording, shouldn't I?
Mic on.
I seem to forget that.
I've already got mine going, so if anyone needs that little bit at the beginning, then it'll be in my video.
Do you send that to whoever requests it? Is that how it works?
Yeah, I mean, I just post them on YouTube and they're public, so I can share the link, however. Send it to people, email, text.
Okay, let's see. Okay, now the recorder's on.
Mic off.
Now I'll reshare the screen. So I'll scroll through the announcements again. Okay, labs. Do anyone of you have questions about any of the labs? If so, now's the time to bring them up. Well, it doesn't sound like there are very many questions. So without further ado, let's go on to the next part, which is the next part of electrochemistry. Although let's have a look at the class project parts I mentioned earlier. Okay, this is what's posted on Blackboard. It's a 2-page PDF, and it describes the goal and the grading, how to submit it, the due dates, some references. So the goals we pretty much went over last time, and that would be to use Excel to compare the residue sequences of the spike proteins generated by the COVID-19 virus, and then some other protein which you will choose. And an example could be the SARS coronavirus spike protein, and that one it's been designated P59594. So and that's posted on Uniprote's website. It's just an example. You could pick anything, like a human virus or influenza virus or some animal coronavirus. Like bats have a lot of them. They're like a coronavirus container. Like they have all kinds of them. And they're also in mice and cows. So any of those are fine. Just try not to pick one that's too different. You want ideally pick one that's as similar as possible so there aren't so many differences. Because one of the goals is to point out where differences occur. And we're like in a drug discovery pipeline, we're actually looking for something that's very similar for which a known treatment exists. So, and the fewer differences there are, the better. And as far as collaborating, that's fine, but don't exchange Excel files. No partners are assigned. The project's individual, but you can talk with one another and work together in that way. But just don't exchange Excel files. And I'll post an Excel file, and that can be used as a starting point. You can change it however you want. And this is worth 5% of the total grade. So that's 50 points altogether. The graph itself is worth 15 points. And it should follow the rules that we've been using for graphs, like have a prominent title, easy to read axis labels, display numbers appropriately on the X and Y axes, should be large enough to fit on one screen and print on one full page, either landscape or portrait. As far as the graph goes, no lines are needed. It's just the data points need to be marked. And all data and calculation should be done on one worksheet, and the graph can be pasted in there with that worksheet. And I'll show you here that Excel file. I put in an example. Here's these two columns here. I just labeled them X and Y for simplicity. Each one of these is around 1,250 numbers long, so it's similar to the length of these proteins. So the line at the bottom is a series of markers. There's zeros, like here from X equals 1, it's the first residue position, to the first 10 are down right here. They're all 0, meaning that they're the same. The two residues are identical. And then on the 11th residue, we start showing differences, and that's what this set of markers is up here. So the goal is just to show a baseline where they're identical and then display a value of 1 for anything that's different. And then this has the canned like default titles and axis labels. Those would need to be improved, like put something meaningful up there for the title and label the axes. And by highlighting the graph and clicking plus, you can add in titles and edit whatever part of the graph you want. So in like these down here, normally those would be 100 units apart and bigger, so they're easier to read. And all that's needed on this axis is a 0 and a 1, also larger, so it's easier to read. So this graph, like let's just pretend that it's finished. But so you just take that and go back to where the data is, and then and then paste it in there. So this is what would be submitted. Like all of this part down here would be filled out. Around 12 or 1300 rows down would just be a bunch of data. The graph would pull from that data and display the markers. And then everything else that's not used should be cleaned out of this page. And you can create any kind of new pages you want. Just click a plus down here. If you need to put something like scratch space, it's fine. Just keep it off the main page. So, and then I'll leave this in. This is the definition of all the residues. And I'll fix this up better and then post it on Blackboard in the next day or so. Are there any questions on that? Okay. All right. Oh, and don't forget to put your name on it, on the graph, and also add references. Now the actual differencing is worth 20 points, and that's all about aligning them properly. And note that when comparing two proteins, that some can have insertions and deletions. So they might be identical up to a certain point, and then one of them might have a deletion. So that'll throw everything off that comes afterwards. They could be identical except for that one, but it'll look like everything is different because they're not lined up properly. So need to keep an eye on that. Make sure to insert spaces as needed so that these things line up appropriately. And like I mentioned, try not to choose something that's going to be a lot of work and that has too many differences, because those don't really have much value scientifically. Ideally, check around for one that shows very few differences. And then displaying the residue formulas, that is, if I go back to that Excel file, that was, let me delete that graph. Displaying the residue is this part here, where if there is a difference, which is indicated by a 1 in column G, then it should display the residue formula for both parties. Like here we have a W and an A. The formula for A is listed, but the formula for W should also be listed. It's just not hooked up yet. And submitting this, send the Excel file by email, and print the graph to a PDF. And to do that, see if we go back to this, let's say we wanted to print this graph. So we should be able to, so you go to File, Print, and then go under the printer options. There's one that says Microsoft Print to PDF. Okay, and then click the print button, and that'll create a PDF file. So we could print that, and it should pop up a save box wanting to know there's your exams. But anyway, it should pop up a PDF save box, and you could save that off and send it by email. And some of these references are pretty interesting, especially this first one. It's not, it's kind of like written halfway between ordinary newspeak and and hardcore science. It's really interesting and explains how the virus originated and also what the status is on developing a treatment. So that's that about the project. Are there any questions?
Mic on.
My sister-in-law teaches an online class that was started because of the shutdown, and she teaches it's like 20 kids on Zoom, and she found out that one of them had taken a screenshot of his face and had posted it there in front of the camera. So while the class was going, it looked like he was intently thinking about what was being said, but he was actually gone. And then so she ended up asking him a question and found out that he wasn't there. So
That is
hopefully none of you are doing that.
No, that's big brain thinking right there.
Yeah.
How old are these kids?
They're about 12 or so.
Oh,
13.
yeah. Okay, that sounds like something my students would do.
Did you say your students?
Yeah, I'm a multi-subject tutor at a junior high, so they're all 12 or 13 years old. So that sounds like something they would do in a Zoom lecture.
Yeah, they're savvy enough with tech to pull it off. Speaking of Zoom, some security holes were found in it. So
yeah, I did also see that.
Yeah, they're recommending everyone at SWIC get off of Zoom. So I didn't get on Zoom because it was owned by Google, and I know Google, it tends to like to collect information and stuff like that. I think Facebook is also part of it, because to create a Zoom account, all you need is a Gmail or a Facebook account, and you can create it. Okay, so that's this, and then let's have a look at, let's see, where were we? The PowerPoint. Okay, so we're back to electrochemistry. So let's continue where we left off on chapter 17. And that'd be here, this. So this is posted on Blackboard. So we'll be following this. Now, one of the fundamental quantities in electrochemistry is called a Faraday. And a Faraday is named after the English scientist Michael Faraday, who lived in the 1800s. And he's a pretty unique fellow in the sense that he received little formal education. And nevertheless, he became one of the most influential scientists in history. And the Faraday unit is named after him, and it's equal to the amount of electricity that must be supplied to a cell to deliver 1 mole of electrons. So 1 Faraday is actually equal to 1 mole of electrons. And now that we're dealing with redox reactions, the reactions explicitly list electrons, so we can relate moles of electrons to moles of gold or silver or copper or any other thing we want to plate out or electrodeposit. This example reaction here shows how gold would be deposited. So we'd have a solution of gold and then give it its electron, could be through an external circuit, and then we get solid gold. For example, here we could have 1 mole of electrons combining with 1 mole of gold 1 ions, and that would yield 1 mole of gold solid, which is here, which is 197 grams of gold. And so what we could do is record the mass of the target electrode where we want to deposit the gold. The target electrode could be a bracelet or watch or whatever, coin. And whenever a certain amount of mass has increased, in this case 197 grams, we would know that 1 mole of electrons have passed through the cell. And as we'll see, we can actually hook a voltmeter up and record the current and measure the time, and we can calculate exactly when to stop the plating just based on current and time. And that's partly based on the Coulomb. The Coulomb is named after a French military engineer and physicist, Charles Coulomb, who lived in the late 1700s. And 1 Coulomb is the amount of electricity delivered by a current of 1 amp for 1 second. And we found this empirically to equal 96,487 coulombs. So that number of coulombs is equivalent to 1 mole of electrons. We normally round that off to 3 sig figs. So we say 96,500 coulombs equals 1 mole of electrons. Another fundamental quantity in electrochemistry is the Ampere. And it was mentioned up here in the definition of the Coulomb. We call them amps for short. It's a capital A. And the Ampere is named after André Ampere, French physicist and mathematician. And the amp is defined as a flow rate of electricity equal to 1 coulomb per second. So like a flow rate out of a faucet would be measured in like gallons per minute. And electricity, whenever we're dealing with that, we use coulombs per second. So 1 amp is equal to 1 coulomb per second. And we have 2 different kinds of cells to do electrochemistry. There's electrolytic cells, and those utilize an external source of voltage placed across the electrodes. And for that reason, we can force non-spontaneous reactions to take place. Like in galvanic cells, that's like an ordinary battery. It has to rely on its own spontaneity to produce a reaction. So like a C battery or D or C cell, those are usually 1.5 volts. There's a manganese oxide cathode in it. Those rely on their own spontaneous ability to conduct electricity. And those would be galvanic cells. So we can use all of these quantities to perform very practical calculations like this one. Like what mass of copper would be deposited from a solution of copper sulfate by a current of 1.5 amps flowing for 2 hours. So let's look at how that would be worked out. There's a PowerPoint showing how we go through the steps. So first step is to take the amount of current, that is the time and the flow rate, and convert that to coulombs. So we have 2 hours duration. Let's convert that to seconds, multiply by 3,600 seconds per hour. It gives us 7,200 total seconds. And then multiply that by 1.5 coulombs per second. That's the definition of an amp is coulombs per second. So at this point, we have coulombs, and it rounds to 11,000 coulombs. So now that we have coulombs, we can convert that to Faradays. Our goal is to get to moles of electrons. So to convert from coulombs to Faradays, we divide by the Faraday constant, which is 96,500, and we get 0.11 Faradays. Next, we convert the Faraday to mole of electrons. So 0.11 Faradays is actually equivalent to 0.11 moles of electrons, according to how it's defined. So now that we have moles of electrons, we can relate to the reaction above. So we have 0.11 mole of electrons, and we can convert that from moles of electrons to moles of copper. Notice the denominator here has 2 moles of electrons, and that comes directly from the redox reaction. The stoichiometry here says that there are 2 electrons involved, so we plug a 2 in on the bottom of that fraction, and we end up with 0.55 moles of copper. So now all we have to do is convert moles of copper to grams of copper. So we multiply by the molecular weight, and we get 3.5 grams of copper. Now, that went through step by step, didn't leave anything out, but we can shorten that. Like there are a couple steps that could be combined, and ordinarily it would be written something like this. So we take our 2 hours, convert to seconds, then to coulombs, then Faradays, then moles of copper, grams of copper. Like the moles, showing the moles of electrons explicitly isn't necessary, because that's kind of absorbed into the definition of the Faraday. So we can go straight from Faradays to moles of copper. So that makes it a little shorter. Okay, another example is how long would it take to generate 25 grams of chromium from a solution of chromium trichloride using a current of 2.75 amps? So to start this one, we take our 25 grams of chromium and convert it to moles. And then we know that for each mole of chromium, we would need 3 Faradays, that is 3 moles of electrons, and that comes out to 1.44 Faradays. Next, we take the Faradays and convert to coulombs, multiply by 96,500. That gives us coulombs, and we know that 1 coulomb is equal to 1 amp second. An amp is defined as a coulomb per second, so if we take an amp times a second, that gives us coulombs. And then we convert seconds to hours, and we get 38.6 amp hours. So an amp hour is a measure of charge. That might sound a little familiar, like ordinary batteries like AA's, AAA's are measured in milliamp hours. So the milliamp hours or amp hours is a measure of the capacity of the reaction or the battery. So we take the 38.6 amp hours and divide out our 2.75 amp current, and that gives us 14 hours. So that would be our answer, 14 hours. Then if we wanted to do this all in one step, like a string of fractions that would be a little shorter, this is what it would look like. We can start out with our mass of chromium, convert to moles chromium, and Faradays, and coulombs, then amp seconds, and then hours. And we end up with 14 hours. Okay. Are there any questions? Next, we have the volt. The volt is named after Alessandro Volta, lived in the late, 17 to 1800s, Italian physicist and chemist. Okay, the volt is also known as the electromotive force, or EMF. And it's a measure of the amount of work that can be done by an electrical circuit. And 1 volt is defined as a flow rate equal to 1 Coulomb something's wrong. There's a typo here. I'll fix that. But it should, a volt is defined as 1 joule per Coulomb. It's not a flow rate. That's a cut and paste error. So disregard that part right there. A volt is 1 joule per Coulomb. It's like this, like if we, in the periodic table, we have the halogens, they all need 1 electron to be stable. Like they like to have like a mole of electrons if we had a mole of fluorine or a mole of chlorine and so forth. And each one of them has a different strength where they can pull electrons from other elements. So it's kind of like the denominator for them would be the same because they all need a mole of electrons, but fluorine has a much stronger ability, like more energy to use. Its numerator would be larger. So we would expect a higher voltage for fluorine than chlorine, which is under it, would be a little lower. And then bromine, which is under chlorine, would be a little bit lower than yet, and so forth. So the volt is actually measuring strength per unit charge. Now to measure this, the different abilities of the elements to attract electrons or just basically take them from other elements, we have a standard reduction potential. And that measures the tendency of an element to undergo reduction. In other words, to gain an electron. If they're reduced, they gain an electron, normally by taking it from a different element. So here are 2 reduction reactions written, 1 for zinc and 1 for copper. Now, if we have both of these possible reactions happening, like the zinc and the copper are mixed together, one of them will be spontaneous and the other won't because they have different abilities to be reduced. So the reaction that's more, or that's spontaneous, is determined by the metal, which is more stable. In this case, it would be copper, because copper is one of the 3, at least like 3 or 4 or so noble metals. They're in the periodic table, it's in column D9. You have copper, silver, and gold all in the same column, and those are our noble metals. So they are good, like they're very stable in solid form. So they like to be a solid. In other words, they like to be on the right-hand side of this reaction right here. So they will readily undergo reduction. So we would expect copper to be reduced when it's partnered with zinc. So what would actually happen is that copper would get reduced and zinc would be oxidized. So we take that first reaction with zinc and turn it around so that it's an oxidation, so it looks like this. So that would be our oxidation half reaction. And the standard reduction potential of this cell would be the sum total of the standard reduction potentials for each half reaction. So we take the E0 value, which is the standard reduction potential, of the substance reduce, which is copper, and add it to the standard reduction potential of whatever's oxidized. That would be zinc in this case. So we take the whatever it is for copper, we could look that up in a table, and we add it to the reduction potential of zinc. And recall we reverse the direction of that reaction, so that introduced a minus sign. So we're actually adding a negative. So it kind of looks like we're subtracting, but we're actually adding the negative. The net result's the same, but technically we're adding a negative. And these values are all measured at unit concentration. And they're tabulated in tables. And here's an example here. This is the standard reduction potentials. They're normally measured at 25 degrees C. There are all these different half reactions, and it shows their relative values. Notice down at the bottom here, we have the elements which are least likely to be reduced. That would be the alkali metals, like lithium, potassium, sodium, and the alkaline earth metals, because those elements like to be dissolved. Like they aren't stable in solid form. So they readily react and give away their electron. So those have very negative standard reduction potentials. If we would switch that around, this would be a positive 3.05, meaning that oxidation of lithium is what's likely to occur, not reduction. But this is a table for reduction, and so everything's listed as reduction. Lithium and the other alkali metals get a negative value. And what's at the top is the elements which are very likely to be reduced. And of course, fluorine's right up there at the top. It has a reduction potential of 2.9 volts. And then here's silver. Silver is one, let's see, silver's 0.8. Here's copper, both versions of it, +1 and +2. Those are fairly high up. I don't see gold listed, but gold would be up above silver. Platinum would be above gold. So those are our standard reduction potentials. And they're all measured at a concentration of 1 molar. And in the case of a gas, the partial pressure must be 1 atmosphere. And the 0 point of the reduction potential scale is a standard hydrogen electrode, which is usually called the She electrode for short. And this electrode consists of a platinum wire inside a glass sleeve, and it's listed in the middle of this chart here. This is the She reaction, or hydrogen gets reduced and generates hydrogen gas, and that's assigned a value of 0. So all of these reduction potentials can be measured against the She electrode. And see, there's a picture of the She electrode in here. This is a Jesperson textbook, which I hope you're reading this, because it does a really good job of describing this. Yeah, here it is. This is a standard hydrogen electrode, or She electrode, where hydrogen gas is piped in at a pressure of 1 atmosphere. And inside there we have a platinum wire. And it's dipped in a solution of 1 molar acid. And so that would be 1/2 cell. Here's the She electrode in combination with the copper electrode. So how the experiment would be conducted is a voltmeter would be connected from one to the other. And the voltmeter does not allow current to pass from one side to the other. It measures like the strength of which copper is tugging at the electrons compared to the H plus. And whenever copper is placed against the She electrode, it'll have a positive value. So here the meter's reading 0.34 volts, and that's what would have been recorded in the table. Here, if we go to copper, it should be at 0.34, like this one. There's 0.34 volts. Okay, so in that reaction against the She electrode, this is the two half reactions which occur. Copper is reduced, and that reaction occurs at the cathode. By definition, that's the positive electrode. It's where reduction occurs. The other electrode would be the anode, the negative electrode, where oxidation occurs. So hydrogen gas is converting into H plus ions and giving up 2 electrons. So it's oxidized. The electrons, like this reaction occurs with a certain force or energy. So it is a top reaction, and the voltmeter records the difference, and they get 0.34 volts. So we can add these two reactions. The electrons cancel, and we get the overall cell reaction here. The E0 is 0.34 volts, and the 0 superscript specifically means standard conditions. So let's look at another reaction. How about chromium against zinc? So if we have chromium and we write its reduction reaction, chromium 3 plus combines with 3 electrons to plate out, makes a solid. That E0 value is minus 0.74 volts. And the same for zinc. For zinc gains 2 electrons, as E0 is minus 0.76. So what happens is the spontaneous reaction is determined by reversing one of these so that the overall sum has a positive E0 cell value. So if we reverse zinc here, switch it around like here, where zinc is oxidized, that's plus 0.76 volts. And if chromium is reduced, that stays at minus 0.74. And if we add those two, we get positive 0.02 volts. So it has a positive value, and that's what would be observed experimentally. And we would need to balance this reaction. You multiply through by 2 and 3 as shown here to get the electrons to cancel, and we end up with 2 chromium ions combining with 3 zinc solids yields 2 chromium solids plus 3 zinc ions. And notice whenever we multiply through by the 2 and the 3, the voltages stay the same because they represent energy per mole. So whenever we multiply by 2 moles or 3 moles to balance this reaction, the energy per mole stays the same. So remember, volts means joules per Coulomb. A Coulomb is the number of moles of electrons. So here's another example where let's find the E0 value for these sets of reactions. So the first one involves aluminum, nickel, nickel sulfate aqueous, and aluminum sulfate aqueous. So let's go down to here. I don't know if you could see that little black box. Oh, pin toolbar. That didn't, okay, it
Mic on.
disappeared. All right, so
Mic off.
let's do the first one, aluminum, nickel, nickel sulfate, and aluminum sulfate. So the idea is to look through the standard tables and find a reaction that involves some of these. We need to include all of them. So we have solid aluminum here and ionized aluminum, solid nickel, ionized nickel. So from the table here, aluminum 3+ yielding solid aluminum has an E0 value of minus 1.67. Now for nickel, its E0 value is minus 0.25. So does anyone have an idea of how we can combine these into a spontaneous reaction?
Mic on.
How about Maddie?
I am not sure.
Anyone else? How about Diana?
I'm not really sure either.
So, are we just looking at A or?
Yeah, just A for now.
Well, it looks like aluminum really doesn't want to give up those electrons. So,
Or it doesn't want to gain the electrons.
oh,
Right.
okay.
Yeah, it's a very negative number for reduction. But you're on the right track. How about Catherine? Are you out there?
Yeah, I'm here. I'm kind of lost too.
Okay. All right, well, how about if we switch one? How about if we reverse that first one? Swap directions. If we do that, the cell voltage would be positive 1.67, and then we add it to negative 0.25, and that gives us a cell voltage of 1.24 volts. So that would be the E0 value for part A. So let's look at the next one. This one's more complicated. It involves lead oxide. So we have lead ion. That's looks like +4. And here we have on the right side here, we have lead sulfate, which would be lead +2. Then we have dichromate ion, H+ from the sulfuric acid. So anyway, if we look through the table of reduction potentials, there happens to be one in there that looks like this, and it includes a lot of the items listed. It has lead oxide, has lead sulfate, it has H+, which would be present from the sulfuric acid, it has sulfate, which would be present from the lead sulfate. So that has an E0 value of positive 1.69. And the table also has chromium, like so far we haven't accounted for the chromium. It looks like here in the potassium dichromate, we would have chromium +6 because oxygen is assigned a an oxidation number of -2, and we have 7 of them. So that means O7 would be -14. Potassium's +1. So we get a +2 there. So we have -14
Mic off.
+2 is -12. And the 2 chromiums have to balance out a -12. So that would make each chromium +6. And over here, each sulfate is -2. So we have 3 of them. So that's -6, negative altogether. It's divided over 2 chromiums. That means each chromium's +3. So we go chromium +6, and then we have chromium +3. So the chromium's either reduced or oxidized from 6 to 3 or the
Mic
other way.
on.
So this is in the table. This reaction, this is a chromium +6, chromium +3, and it has acid present. And that has a standard reduction potential of 1.33. So how can we make this one spontaneous? Like, what would the actual cell voltage be? How about Jacob? Are you there? No. How about Elizabeth?
I'm not really sure, but you could maybe reverse the bottom one. I don't know.
Okay, that sounds good. Yeah, so let's reverse the bottom one. It gives us an overall positive number. So 1.69, and adding to negative 1.33 from the reverse reaction gives us a positive 0.36 volts.
So why do we reverse the bottom one?
Because the other reaction has a greater positive value.
Okay.
So the only way to combine these reactions and end up with a positive voltage is to reverse the second reaction.
Okay. So the first one wants to be reduced more, and so it gets reduced, and then the other one we have to reverse.
Right, we reverse and oxidize the chromium.
Okay.
Yeah, we oxidize chromium 3+ here and end up with 6+ over here in the dichromate. Okay, the next one involves silver and lead. It's a little more straightforward. By the way, some of this in part B is what goes on in an ordinary car battery, like a lead acid battery. Okay, so this one we have silver has a E0 of 0.80, and then we have lead, E0 of -0.13. Okay, how do we combine these to make a positive cell voltage?
Do you reverse the bottom one?
Yeah.
Okay, let's try. Yeah, reverse the bottom one. Yeah, so we get 0.80, and then we add it to the reverse reaction, which makes it positive, and we get 0.93 volts. Okay, the next one is manganese and chlorine. So MnO2, which by the way is what's in ordinary flashlight batteries, like the AA, AAA, C, D batteries normally have MnO2 in there. And when combined with the anode, which is usually carbon, it has a voltage of 1.5 volts. But its E0 value, though, is 1.28 against the She electrode. So the other is chlorine, which is 1.36. Okay, so how do we combine these? What about Brennan?
Reverse the top one.
Okay. Yep. Okay, that gives us 1.36 plus the negative 1.28, which is a positive 0.08 volts. Okay, the last one is manganese solid to Mn2 plus, and then we have H plus and H2. That looks like the standard hydrogen electrode, H plus and H2. So there are two half reactions. Now we need to combine these. This one's kind of tricky. Any ideas on what to do here? Because we have a 0, it's not going to change anything if we reverse it.
So reverse the top one.
Well, it's if we reversed it, yeah, it's still, we can't really reverse it because it's measured against the She electrode. Yeah, so we can't reverse that one. This is non-spontaneous. It's negative 1.03 volts.
Mic off.
Okay, so that's how we combine our half reactions into a spontaneous cell reaction. So this is like predicting which way a reaction will run when it's hooked up into an electrochemical cell. Okay, so let's go back to where we were at. We were on page 5. Now let's go on to spontaneity of redox reactions. Now we worked a lot on spontaneity in chapter 16 with the Gibbs free energy. And we have our expression delta G is equal to delta H minus T delta S and so forth. And we also found that delta G is equivalent to the maximum amount of work obtainable from a chemical reaction. So we could say delta G is the negative of the maximum work done by a system, because delta G needs to be negative to be spontaneous. So hence the negative sign there, and the work done by the system would be like a gas expanding. So we're let's say like in a airbag in a car, a solid spontaneously generates a gas. So the final volume is much greater than the initial volume. So we get a positive delta V. So P delta V would be positive. And we have that negative sign there, which makes it negative. And a negative delta G means it's spontaneous. So the definition of work, if you've taken physics, you know it's defined as force times distance. And in chapter 16, we adapted that to chemistry and dealing with gases by dividing by the area and multiplying by the area, like basically playing around with these units. So we get pressure times displaced volume, or P delta V. So we have PV work, is what we called it. So now we can do the same thing, and we have energy, which is the unit of work per Coulomb, and times the number of coulombs. So that'll give us a total amount of work. And that's equal to the cell voltage, the E cell voltage. It's literally the volts is joules per Coulomb. That's what this first term is, times the number of coulombs, which is N times the Faraday constant. So NF is the number of coulombs. So this gives us an expression for delta G inside a cell. Delta G is equal to minus NFE. And when all of the species have a concentration of 1 molar, we put a superscript on the E to get E0 of the cell, and that makes delta G the standard free energy change that we've been dealing with all along here in chapter 16. So delta G0 is a standard free energy change, and that's equal to minus NF E0. So from this, we can calculate delta G from the cell voltages. So we have here the copper zinc reaction. The zinc is oxidized, and that reaction has a potential of plus 0.76 volts. And then the copper is reduced, which has a value of 0.34 volts. So if we add these two reactions to get the overall cell reaction, that is positive 1.1 volts. So now we can figure out what delta G is for that cell reaction. We plug everything into this expression. The reaction involved 2 moles of electrons here. So N is 2. Faraday constant is 96,500 coulombs per mole of electrons. And then plug in our cell voltage, which is 1.10 volts. And all of that comes out to minus 212,000 joules. So it's pretty handy. That tells us whether or not a reaction is spontaneous based on the cell voltages. Most of the time we can tell that already by looking at the cell voltage, but this puts it on more fundamental, like chemical terms through using delta G. Now, in chapter 16, we also had an expression for what was called the thermodynamic equilibrium constant, and that was the value of K that was calculated from delta G and or like delta H and delta S. So we call those thermodynamic equilibrium constants, as opposed to something that's measured, like this. The tables of KAs and KBs are measured, but we can calculate them. To keep them apart, we call them the thermodynamic equilibrium constants. So we can combine this with the expression we found earlier, delta G is equal to minus NFE. We can combine that with what we did in chapter 16 to express the equilibrium constant in terms of the cell voltages. When we do that, we end up with this expression here. And notice that parentheses contains a set of physical constants. R, T, and F are all constant at standard conditions. Like the T temp becomes a constant, which is 298 Kelvin at standard conditions. So we can plug all that in. We have our R is 8.314, temp's 298, and the Faraday constant's 96,500. Plug all that in and we get 0.0257 volts. So now we can simplify this expression that we had earlier and say E0 of a cell is equal to 0.0257 on N times the log of Kc. So we can solve for Kc. Take this equation, rearrange it to get Kc by itself. And For the copper zinc reaction, we could plug everything in. So we have N is 2 moles of electrons. E0 cell is 1.1 volts, and divide by that constant of 0.0257 volts, and we get 85.6. So if log of K is 85.6, we can take the exponential of both sides and solve for K, and that's 1.5 times 10 to the 37th. So that's a really huge value. And that shows that it is an extremely spontaneous reaction. So this cell reaction up here, we've been looking at this zinc copper cell reaction is extremely spontaneous, and it goes essentially to completion. So the K value, or reaction quotient for this at standard conditions, is extremely large. So it means the right-hand side totally dominates. The left-hand side, or the reactant side, is very tiny. Okay, so now for concentration effect on cell potential. Like in chapter 16, we accounted for conditions other than equilibrium by using this expression, delta G equals delta G0 plus RT log Q, where Q is a reaction quotient, and Q is only equal to K at equilibrium. So we're really interested in finding out how the cell voltage changes at other concentrations other than 1 molar. That the table was only valid for conditions of 1 molar. So in real life, we have concentrations all over the place. So we need something to account for that. So we can adapt this expression like we did before, substitute in minus NFE for delta G, and rearrange things, and we get what's known as the Nernst equation. And the Nernst equation is E equals E0 minus 0.0257 on N times log Q. And sometimes it's written in terms of base 10 logs. And in that case, this constant would be 0.0592, and it'd be multiplied by the base 10 log of Q. But we've been working with natural logs, so this is written in terms of natural logs as well. So for this zinc copper reaction, we can plug in everything here in terms of concentrations, and we get the Nernst equation for that reaction. So it's E is equal to E0 minus 0.0257 divided by moles of electrons, which is 2, times the natural log of the concentration of zinc 2 plus divided by the concentration of copper 2 plus. So with this expression, we can calculate how the cell voltage changes as a function of concentration. So for example, if the zinc is 0.4 molar, the copper is 0.02 molar, we can substitute that in, and we end up with a cell voltage of 1.06 volts. So the concentrations changing from 1 molar did affect the cell voltage a little bit by about 6%. So this shows how the concentrations change the cell voltage. And we'll work through quite a few examples of that next week. Okay, are there any questions on this?
Mic on.
Not on this specifically, but for the exam later, are we going to have an equation sheet, sort of like some of the other ones?
Right, yeah.
Okay.
Yeah, I assume sort of that the equations are available since it's open book, but I can include an equation sheet like the first exam did.
Right.
Yeah, it'd be handy to have them all in one place, like all of these here, like this one here.
Yeah. I don't know about anyone else, but it's just very like extremely tough for me to follow like all of the equations and everything unless I have them like right in front of me.
Okay. Yeah, that's fine. I can include them on a sheet in the test. So how are you all liking the online stuff?
Not really
In
a fan.
love with? Oh, yeah, I can relate.
But I never liked online classes, so.
Yeah, especially with the labs. Especially with the labs. There's nothing really that can replace being there and actually doing it with your own hands.
Right.
Okay. Well, is anyone having I'm just mentioning this in case if anyone's having difficulties like with the online transition and like adapting, and I know it's not easy, but there is a program set up by the Success Center called Project Success where they have things like I'm not sure if they use Skype, but it's like a Skype, or maybe they use Teams now, but where you can hook up a connection to a tutor there and they can help out, or they can do it by phone or email. So if anyone wants to be referred to that, let me know. Just send an email. It's called Project Success. Like from the quizzes that were turned in, it looks like you have a pretty good understanding of Chapter 16. So, but if you do run into difficulties and want to be referred to that program, just shoot me an email, let me know. Okay, well, that's about all I had. So we'll finish a little bit early.
All right.
I'm not sure, can you communicate with one another on Teams outside of a meeting? Like any of you can get on and request a meeting with someone else, right?
Yes. Yes.
Okay. Yeah, just log in, and if you know the other person's email, just set up a meeting and then you could have a video conference session with them.
Yeah, it's kind of like a Skype call. We're able to do that, so.
Okay. All right. Well, okay, I guess we're all finished. So I'll see you next week. Have a good weekend.
Yep.
Bye.